Hello everyone and welcome to my YouTube channel. And in the last video you have seen we have make a code and we have run it, and we can see different things like different plots like mass flow rate, COP and pH diagram. So now we will move further on, and now we will like to add looping in it. So in looping, we can we want to know actually when we do this type of simulation, like how these refrigerants behave when certain things change. For example, the evaporator temperature or the condenser temperature changes, how the COP of these refrigerant vary. So for this we need to loop this program, and in loop actually it runs on changing the evaporation temperature, and it calculates on every loop the value of COP or any other parameters which you want to calculate. For example, you want to measure how the mass flow rate changes with the evaporator temperature change, how the condenser temperature with changing the condenser temperature, how the mass flow rate or COP varies. So in this video we will see how this looping uh, we can make looping code. So for this we will just ask, what we need is please modify this code to make loop code. I need the evaporator temperature to increase from, suppose, -10 to 20 degrees Celsius, and I want to see how the COP of all these refrigerants vary with this temperature change, right? So for this, how we want to see this, please make a plot of COP which will be on y-axis versus evaporator temperature which will be on x-axis for all the refrigerants in one plot. So let's see, does Grok understands what we want, and will it provide us the required code. So here it is saying it will modify the previous code and include a loop which we need over evaporator saturation temperature from -10 to 20 degrees Celsius with a 5 degrees Celsius increment to analyze how the COP varies for each refrigerant, and the code will retain 5 degrees Celsius superheating. Subcooling will use cool probe, and instead of previous pH diagrams and bar plots, it will generate a single plot of COP versus evaporator temperature for all the refrigerants using the colors of each. So from here it seems like it understood what we want. So let us copy the code and just make a new file and just name it grok 3, and just paste this code and run it to check it has provided us the desired code or not. Yes, we can see, like from the graph, it has provided us the correct code. So here on the x-axis, you can see this is the evaporator temperature changing from -10 with an increment of 5 degrees Celsius up to 20 degrees Celsius. So here one thing you should note, like all other parameters, for example superheating, condenser temperature and isentropic efficiency, they are constant. And here you can see how with the increase of the evaporation temperature the COP is increasing. So why it is increasing? Because the temperature lag or the temperature shift or the temperature difference between the evaporator and the condenser is decreasing. As the evaporator temperature is increasing, the condenser temperature is fixed. So when the evaporator temperature increases, this temperature difference is decreasing, which is increasing the overall system efficiency and COP. So the important thing is that we want to see which refrigerant is performing better, or is there some change as the evaporator temperature increases. For example, you can see from this graph that R410 is continuously having the least COP. So throughout the evaporator temperature change, and the next is R32, it is also having the second least COP values. But here it's the important thing, you can see ammonia is having the best COP values. And as the evaporator temperature increases, you can see like this R134A is also having the similar COP values. So these are some interesting results which you want to see and you want to simulate, and if you are doing some research study. So this is the basic point from where you start coding. And so here you can see how these are varying, and these are some interesting results. So from here you can depict like ammonia is similar at 20 degree evaporator temperature as of R134A. So next, what we will like, we also want to save these results in Excel sheet. So we will just ask him also save these results in Excel sheet. So it will just save the results in Excel sheet. So it will revise it, and additionally it will also save this result in the Excel sheet. So actually you want these type of when you are writing these type of codes, this one is a simple code, so it does not have very large data. So but actually when you are working on some big programs, so you need a lot of data. Like for in this case we are just having the COP values as the evaporator temperature is changing, but you are, when you are having some detailed coding, you will also save the mass flow rate values, how they are changing, or if it has some like relation with isentropic efficiency, how the isentropic efficiency is changing, how the compression ratio is changing, how the pressures are changing for the condenser and the evaporator, how the temperature you are varying. So some fixed variables or parameters and some changing parameters. So in that detailed coding you check all how they vary. So for that actually you need to save your results in an Excel sheet also. So here you can see it has add save the results to Excel sheet, and it has results, evaporator temperature, COP, mass flow rate, compressor work, and condenser heat rejection. So it has saved all the points, and from here you can see it has also saved the state points. So let's see, just copy it and make a new file. It's better to make new file because sometimes if you paste it on the similar file, so it's not actually correct code. It's always better to make another new file and just run it and see. So here you can see it has provided us the similar uh, plot, and it is saying like the results are saved with this file vcc results. And now let's see. Here we can see on the same uh, folder it will save the excel file, and let's see how it has saved the results, and we will try to modify it if we need to. So here you can see in the excel sheet, with this evaporator temperature changing, it has saved all our results of COP, mass flow rate, compressor work, condenser heat rejection, and all the state points, pressure, enthalpy, entropy values. So simply you can see how you can also save these results. So in Excel you can also, like if you want to plot, you can also plot these results, right? It is also very easy to plot in Excel all these results like this. So here you can see this is for R134A, and then you can plot it for 410, 32, and ammonia. So it has saved it on different tabs. But what we are doing, if we have a lot of data, you sometimes come to Excel and you make your own plots. But for small programs, you can just ask it, it will plot it for you. So in this video you see how simply we can just get this looping, and how with looping we can just generate different graphs, and also how we can save these graphs, points and data in Excel sheet. So that is all for this video, and in the next video we will see how we can further go in depth for this looping, and how we can make our simulation program more advanced so that we can use it for our study purpose or for our research purpose. Thank you very much for watching this video, and please like and subscribe if you like it.